Power series 9.8. If x is a variable, now we're introducing variables into our series stuff. If x is a variable, the infinite series where I have my a sub n, which is what I always had, times x or x minus c to the nth power, for the x is called a power series. And you just see as your counter changes, you get the next term, and those will be coefficients that are functions of n. And now x to the 0, x to the 1, x to the 2. You see, I'm creating a polynomial out of an infinite series. If it's centered at 0, it's called a power series. If it's centered at c, all of the x's become x minus c's, and I have a power series centered at c. Okay? Think back what we just did in the last section, Taylor and Maclaurin's polynomials. If we look at them as infinite, if n goes to infinity, then, like I just said, we can see the pattern and we can come up with a function of n that represents all of our a sub n's, and we can write these polynomials as infinite series. And that opens up a whole brand new world, because if you can take some other kind of function, exponential, logarithm, trig function, and use its derivatives and find a power series that approximates it, now you just have a polynomial. And polynomials are easy to use when you're doing calculus. So some things that couldn't be done otherwise can now be done using the power series representation of your function. And this slide just says what I just said. However, some of these power series that are centered at c or 0 or whatever will conform to that curve from minus infinity to plus infinity. Some of them will only conform to the curve for a short distance. So our job is to figure out the interval about c for which our power series is correctly approximating, and so where our series converges and looks like our function. So we've got to use a test for a power series to find the radius of convergence. In other words, there is, if we're looking at the x values here, here's c, there's going to be some radius that we're going to go out, or that way, or that way. So once we find the radius of convergence, then we'll know the interval of convergence, and it's always centered at c. And you can look at these polynomials and know where their center point is. Once we find the interval, we're going to need to check the endpoints to see if our power series converges at the endpoints. The way that we find our radius of convergence is my very favorite, the ratio test. Just be careful. Sometimes the root test, but most of the time we will use the ratio test. And because there's an x in there, and because the ratio test uses absolute value, we end up with these absolute value inequalities. Because for the ratio test to be convergent, to show convergence, that absolute value has to be less than 1. So let's try one on for size. Given this series right here, you see that we have x to the n, and what that means is, because it's plain old x, we know that we're centered at 0. So let's plug and chug and see what happens. The ratio test is the limit as n goes to infinity of the absolute value of the ratio. You're going to copy your guy, ignoring the alternating part because it's absolute value. Copy the a sub n in the denominator, with the x sub n, and then add 1 to all of the n's in the numerator. So if I add 1 to this n, I get n plus 2. Add 1 here, I get n plus 3. Add 1 to the power, I get x to the n plus 1. So you're going to invert the bottom and multiply, and the x to the n plus 1 will then multiply n plus 1 times n plus 2. And the x to the n that was in the denominator is going to be multiplied by the denominator of the top, and we get this. And now we see that the n plus 2's cancel. The x to the nth power will cancel all but one of the x's in the top, and we're going to be left with x n plus 1 over the n plus 3. Now we take once we get this simplified as much as possible, we take the limit as n goes to infinity. Now, the n going to infinity doesn't affect our x. It only affects this part. And you see that n over n, the plus 1 and plus 3 are negligible because we're going infinitely large. And the n's cancel, and we get 1 times x. And here is after you take the limit. Now remember, the ratio test says that you're convergent for the absolute value and the limit being less than 1. So the less than 1 part comes after the limit, and this is what's required for our series to converge. So once we do this, we have a new equation or inequality. We have absolute value less than 1. Well, what does that mean? It means that x is in the middle, and I go to the right 1 unit and to the left 1 unit, and I get this inequality here. Now, when we get this right here and x is all by itself, that number right there is our radius. It's not always 1. Sometimes we have x centered at a different value, and we'll have to get x minus c in the middle. And sometimes we have numbers multiplying the x, and we'll multiply, divide, whatever we have to do to get x or x minus c by itself. So this is not always 1 at the end of the problem, and you'll see that in your homework. So once we get this number when x is by itself, that number is my radius of convergence. And we see that if I start at 0 in the middle and I go to the right one and to the left one, that my interval of convergence is minus 1 to plus 1. However, I also have to do the tests that we've already learned in this chapter to check my endpoint. So for x equals -1, I go back to my original series and I change that x to be -1. And I wrote it out for you here. So I've got the -1 to the n that was in the original question. And now if x is -1, he's raised to the n as well. When I multiply these two guys out, I get -1 to the 2n. Well, 2n is always even. And so that guy is always just plain old +1. The bottom stays the same, and now I've got this new series that I have to do a test for. So if I multiply out the bottom, you see I have an n squared. So I choose to compare to the convergent p-series 1 over n squared. I'm using the limit comparison test. You can do what you want to do, but limit comparison test is always so easy. And reminder that when you're doing any comparison test, you have to compare to the right thing. If you compare it to the wrong thing, you get you get an inconclusive test. So I see that my power on the bottom is n squared. That other n isn't, and the +2 at the back aren't going to matter when n is infinitely large. So you just look at the highest power in the denominator, and that's what you compare it to. So here's my ratio, and you know what? I messed this up. I'm going to fix my notes right here because that, hold on, my thing's too big. That is not an absolute value. The absolute value comes in the ratio test. The limit comparison test doesn't have an absolute value. Okay, so I've put the ratio of one thing to the other here, and I'm taking the limit as n goes to infinity. invert the bottom and multiply. Now I've got n squared over n squared plus all this stuff. The limit as n goes to infinity is going to give me exactly 1. So 1 is positive and finite, and so this series, my test series, is convergent by the limit comparison test. Now I take the other endpoint, the positive one. If x equals positive 1, by the way, that being convergent at that endpoint means that that endpoint is included in my interval. That's why this is a box instead of an open parenthesis. I'm going to equal the negative 1. All right, if x equals positive 1, in the original, that's just 1 to the n. You can ignore it, and you get negative 1 to the n divided by the stuff. You get this. Now, if this is an alternating series, I'm not worried about absolute or conditional convergence for this particular problem because it's part of something else. So I can just do the limit as the absolute value goes to infinity. It's the alternating series test. If you get 0 and it's alternating, then you know that it's convergent. So I'm including both of my endpoints. Okay, let's try this guy. Now notice that I've got a power in the top and a factorial in the bottom. Just be really careful. Another thing to pay attention to is that this n is being multiplied by 2. So when I add 1 to the n, I have to distribute the 2, and I'm going to get 2n plus 2. Okay, now this x right here you see is centered at 0 because there's nothing being added or subtracted. So I get my center point. I take the limit of the absolute value of the ratio, always the same thing, right? Copy the a sub n x to the n in the denominator. By the way, you do see that that's a sub n x to the n, right? Let me make a quick little note of here to the side. The top of that is 3 to the n x to the n, because the if you're multiplying in there, then inside the parentheses, then both the 3 and the x get the exponent. And the bottom is 2n factorial. So you have a sub n is the 3 to the n over 2n factorial. Not that it matters much, but you need to see that that x to the n is separate, okay? I'm not going to separate it when I work it because I don't have to. All right, here we go. We've got the original in the denominator. I add 1 to that power to get that. I add 1 to the n to get this. I'm going to invert the bottom and multiply. So the denominator swings up to the top, and I get the 2n factorial up here. This 3x to the n is going to go into the denominator from above. And so the top has the 3x to the n plus 1. The bottom has just 3x to the n. All of these on the bottom will cancel the n of these, and we're left with just 1 3x in the top. The factorials. 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n factorial. Those are going to cancel, and we're going to be left with just these two on the bottom and the 3x on the top, and you see that right here. These are just fun because they're busy work and they're not difficult, and it's just so satisfying when it works out. So the stuff that gets left over is going to be, we're going to take the limit. These n's in the denominator are going to cause that fraction to go to 0. No matter what x is, if the denominator is infinite, then this is going to go to 0, which is always less than 1. So this particular problem converges absolutely for all values of x. So you see its radius is infinite, centered at 0, and its interval is minus infinity to plus infinity. Okay, here's a good one. check out this x minus 1 here. If it's not x to the n, if it's blob to the n, then this thing is centered at the point, at the x value that makes that 0, the number that you're subtracting, right? So we get that we're centered at positive 1. This will be good if we get a number, but we're not going to get a number, so boring. All right, ratio test. The limit to infinity of the absolute value of the ratio, and you put the original in the denominator. This 2n factorial becomes 2n plus 2. I've already explained that. That power goes up by 1. That power goes up by 1. Taking the denominator, flipping it, and we see that we've got 5n over 5n plus 1. All of the 5's cancel on the top, and we're left with 5 on the bottom right here. The 2n factorial is going to cancel the 2n factorial after I've peeled off the first two factors. X minus 1 to the n cancels all but one of these x minus 1's in the top. So what am I left with? I've got the 2n plus 2, 2n plus 1. I've got one of the x minus 1's, and I'm left with just a 5 in the denominator. So when we take this limit as the n's go to infinity, it doesn't matter what x is, you see that this limit is, these n's are going to infinity. The whole thing blows up. Now, it only converges if this thing is less than 1, right? So if all of these n's are going to infinity, then the only place where this guy right here is going to be less than 1 is if this guy right here is 0. So this only converges at C. All of your power series approximations will be convergent at C. It's just how far out. What is the radius of convergence? And in this case, that's never going to be less than 1. So our radius is 0, and we're convergent only at the C value itself.